start. Today, Wenjun Niu from the Perimeter Institute will give his second lecture about quantum algebras and R-matrices from equivariant affine Grassmannian. So please.
Yeah, thank you very much. So yeah, last time I kind of stated the main results, so this is the to-do list for this time, and much we'll be able to go through, but this what I have planned. Let me recall towards the end of last time, the idea was to look at this equivariant affine Grassmannian and construct fiber functors using splitting of Lie algebras. And the observation is that a splitting of Lie algebra gives rise to a fiber functor, and moreover gives rise to a Lie bialgebra structure on the cotangent. And the main theorem we want to state is that for each such splitting, one gets a Hopf algebra. And moreover, for different splittings, the resulting Hopf algebras are twist equivalent. As expected, because they come from the same monoidal category. And lastly, that there's some uniqueness statement. If you assume that the Lie algebra you start with is simple, and you require the quantization to respect not just loop grading, but also another grading coming from this cotangent. So that's the main theorem. And I won't really talk about this uniqueness, but I'll in the following, I'll sketch the construction 1 and 2. So that's the
Maybe you recall the setup, like the notation. I mean, of course, you should not assume that people remember what is G of K and so on. Just very briefly.
Yeah. So very briefly, I have the Lie algebra G of K. Let's recall that.
Zhongzhu, there is an echo from your second device. Can you? Yeah.
Thanks.
Okay.
So I think I can still hear the echo. Okay, thanks. So so for a Lie algebra G, we consider the sort of a perturbative version of the equivariant affine Grassmannian, where we replace the group by their formal group. And what I would like to do is to study the
I'm confused. This G, is it a group or a Lie algebra? Because
it's a Lie algebra.
It's a Lie algebra. Okay.
Group.
So
and I treat them as formal groups.
Okay.
And so we would like to build fiber functor using the splitting of the Lie algebra G of O inside of G of K. So in a complementary Lie Saba algebra. From each of the splitting, we're going to construct a Hopf algebra, which is what I call UH bar D of O. And it quantizes the Lie bialgebra structure on T star G, given by this Lagrangian splitting. So this D is the cotangent of the Lie algebra G. All right. So does that suffice or?
Yeah, for me it suffices, but people are free to unmute and ask questions.
Yeah. Just a quick, the D is the cotangent bundle of the finite dimensional Lie algebra.
Sorry, I couldn't hear you well.
Finite dimensional Lie algebra.
Yeah. G is a finite dimensional Lie algebra.
And the cotangent bundle of the finite dimensional Lie algebra.
Right. So this is the as a Lie algebra, it's just the semi-direct product G and G dual.
Yes.
Thanks. Yes. So it turns out that quantization of D of O is related to this double quotient. Okay, so let me first construct the quantum algebra.
Sorry, and your notation, you take this double quotient, thinking of G of K as a formal group, yeah, or what?
Yeah.
Formal group, topological, or just do you need any topology like Tate topology or?
Yeah,
No.
so right. So your the G of K is technically a topological in the algebra. So the formal group is really a end formal group. If
Yeah,
you
and what stands on the left is what? Coherent shifts? I cannot even understand it. Because it's unclearly. You take what? Coherent shifts or what? Fiber functor from what category?
so from the category of coherent shifts. So coherent shifts of formal
so
scheme.
that's-
If this formal scheme is affine, if it's the ring of functions on the topological ring, then this is just the category of finite dimensional smooth modules.
Yeah, but do you take any derived category or you take just Abelian category of?
For the construction to follow, Abelian category suffice, but yeah, you can of course take the derived category in the end.
Okay.
Thanks. So the idea is the following. So once I have this, so okay, so let me first say the construction of this algebra. As an algebra, it's just given by the following simple observation that once I have the splitting, I can replace GO equivalent coherent sheaths on GK mod GO by GO equivalent coherent sheaths on H. And that's the same as modules for GO equivalent modules, whereas meaning a module for the universal enveloping algebra of G of O, semi-direct product functions on the formal group. And of course, we can replace functions on H by...
Excuse me again. When you say coherent shifts on double coset, it's the same as coherent equivariant coherent shifts just on the formal neighborhood of the unit in the affine Grassmannian. Is it the same?
Yeah, it's the same as sort of the formal
Yeah,
group equivalent
okay.
coherent shifts on the yes.
Okay, thank you.
Yes.
So there are no deriving or just the
Right.
coherent shifts, no deriving.
Yeah.
Okay.
Yeah, right now you don't derive anything simply because like when you restrict to this formal neighborhood, everything is the monoidal structure is exact. It's nothing. You can first take the Abelian category and then derive it. Yeah. So now we're going to identify the functions on H with the symmetric algebra of G star of O. Now I'm going to introduce an H bar, and I'm going to comment on this. So here we're using the identification, the dual, the pairing between GK mod GO, which is H, with G star of O, but I'm going to insert an H bar so that I can talk about add this formal parameter. And this pairing is just a residual pairing. I take an element here, times an H bar T. I get the pairing just given by the residual of the canonical pairing. So the reason I add this H bar, first of all, is so that I can talk about quantization as a family, so that I can take limit H bar equal to 0 to get the classical result. But moreover...
sorry, I'm confused. You multiply by H bar. How do you get the series?
Oh, you don't get series here, but you get series if you have H bar here.
So then you should write it here because.
Yeah. So the reason I introduce H bar, first of all, is so that I can talk about this flat, this family of deformation. But moreover, this allows me to say that the dual of symmetric algebra of H being an infinite dimensional vector space, its linear dual should be a completed symmetric algebra. But having this extra degree order of H bar, then the dual of this now sits inside symmetric algebra of H dual with an H bar order parameter, so that I don't need to also complete in a symmetric degree. So that the formula is now finite in every H bar degree. It's just infinite in orders of H bar.
So what dot?
H dot is G star of O. So if I don't include this H bar, I not only have to complete in the H star O direction, I also need to complete in the symmetric degree direction. So this is understandable because when you consider coherent sheaves over this formal scheme, you're really considering smooth modules, and smooth modules are modules where the symmetric powers also act nilpotently. So if you want to set H bar equal to 1, you have to complete in both these degrees.
Okay.
Yeah. So now we have set up this algebra. Now we can define the Hopf structure.
So just a quick question in this the right hand side of the symmetric H is that H star A, and with the H bar. So H bar is really including the adic, because D has a unique maximal ideal. Is that compact?
Yeah. So this is going to be a
including the adic completion.
Yes. It's including. So this H bar, first of all, encode this sort of the symmetric completion.
Okay.
And then also.
Oh, that's the symmetric completion, but G star D has also, because D has a maximal ideal. Here.
Yeah. So in particular, when I set H bar equal to 0, and I get back to the classical limit.
So the dual here really means as a dual over C or over O. That's
so this G star here is G star over C. Is that what you mean? It's H star.
Yeah. Here. Well, yeah, but you're taking value at O. That's it.
Yeah.
G star O, right?
So yeah, I'm saying that the linear dual of H is G star of O. Yeah.
Okay.
Great. Thanks for the question. Yeah. Any other questions? Now, if not, so we will now construct the Hopf structure on this algebra, and it's constructed by just looking at the monoidal structure on this equivariant affine Grassmannian. So the monoidal structure is given by the convolution diagram upstairs. You pull and push, and we now rewrite this diagram everywhere. When I see a GK mod GO on quotient on the right, I replace that by H. So I get a simplified diagram which looks like this, and then the corresponding monoidal structure is just the pull-push along these maps, and then we just need to rewrite them in terms of modules for the algebra that I just talked about. And there are two parts. The first part called 1, the second part called 2. I'm going to start with the easier one, which is 2. If we look at what number 2 does, it's just push forward along this map, which is just multiplication on H. Since here is just, again, multiplication on G of K. So if I ask what is the corresponding map of rings, is precisely the coproduct on the symmetric algebra due to the group multiplication law. So number 2 gives a coproduct on the symmetric algebra of G star of O, H bar, due to the group law or the algebra multiplication of U of H. So in other words, this is just the Baker-Campbell-Hausdorff formula. And here, having this extra H bar in the pairing makes sure that the coproduct of an object here still lives in here. I don't need to complete in symmetric degrees. Okay, so that's the second part.
So what is BCA? I cannot read it.
Baker-Campbell-Hausdorff. Yeah, let me just.
Okay.
Formula. So this is just saying that when you have a group or a formal group, it's functions and form a Hopf algebra, where the coproduct is due to the group multiplication law.
So the action basically is as a group action, not as the algebra action.
No. Yeah. It's a group action. Yeah, exactly. Sorry, I should say that this semi-direct product. If I were to use the Lie algebra action, this would just be this is not a quantization. It's just the origin.
Yeah.
This action is really the group action of G on H, which is sort of in some sense of the quantization of the Lie algebra action. Yeah. Thanks for that comment. So number one is more interesting because it sort of sends identity on H times H, but maps this GO copy into the action, basically of these two actions of G of O. So it's giving a coproduct to G of O, but it's a very interesting coproduct because this G of O action on this H times H is very interesting. It comes from this identification because take two elements, an element X in G of O, Y and Z in H. Let's make them into group-like elements by exponentiating them. Then I can ask, how does this act on this two element, e to the H bar Y and H bar Z? And then on the first factor, you just act because nothing happens there. But then when you want to act on the second factor, you have to first commute the first factor past each other using this identification in this arrow, and this will make the e to the H bar Y act on e to the H bar X. So the resulting formula look like this. So this is how this copy of G of O acts on this formal group. So you act on the first vector just trivially, or as it should act, and then you have to commute these two. And when you commute, this H bar X get changed to something modified by H bar Y. So this actually is a coproduct on X, which is given by delta of X is X tensor 1 plus phi tensor Xi, where phi are element in the symmetric algebra of G star O. In other words, they're functions on the formal group such that if you pair it with a group-like element, let's say it H bar Y, this becomes the action of e to the H bar Y on X. So this is precisely just looking at how this, under this identification, this equivariant structure change. And the claim is that these two formula glue into a coproduct. And the rest of the Hopf structure is clear. So and this coproduct quantizes delta H. So that's the construction of this Hopf structure. Any questions? Great. The second part, the first part is that there is such a Hopf structure. It does quantize delta H, and it's clearly just coming, it's just by definition coming from the equivariant monoidal structure of the equivariant affine Grassmannian. And therefore, given two different splittings, we should be able to construct a Hopf twist between the two Hopf algebras. And it's given now, now I'll sketch how we construct this Hopf twist. The idea is the following. Suppose I have this Lie algebra H. The important part of this construction is that I have an embedding of the universal enveloping algebra of H into the universal enveloping algebra of G of K. Embedding is a linear map. So now this linear map can be thought of as a tensor, and this is going to show up many times later too, that I can think of this as a tensor series in the following vector space. Namely, this is just saying that sort of a section, a map from the group to this UG of K is the same as a function on the group valued in UG of K. And this is a tensor series, and moreover, this tensor.
Just a quick question. So the UG of K, so the universal enveloping algebra, you're taking over the field of complex numbers.
Yes.
As a
so
steady
here,
algebra.
Yeah.
Okay.
Without speaking, this is always taking over complex numbers. Yeah.
Thank you.
And this is this should be understood as the topological completion of the universal enveloping algebra of G of TT inverse. Yeah. So the series is sort of what defines, and I did the embedding of the Lie algebra of the universal enveloping algebra. So in particular, it satisfies the following two properties. First of all, if I coproduct the first factor using the coproduct on this defined by this Baker-Campbell-Hostall formula, then it satisfies that this is epsilon H13, epsilon H23. And this is just the statement that this embedding is a map of algebras, because this coproduct is due to the algebra multiplication. Similarly, if I consider one tensor delta epsilon, here this delta is the symmetric coproduct on U of G, then this is equal to epsilon 12, epsilon 13, which is also equal to epsilon 13, epsilon 12, simply because the symmetric algebra is commutative. So here, multiplication is happening in this algebra. The second statement is just the statement that U of H is this embedding is a map of Hopf algebras under the co-commutative coproduct. So it turns out that I get one of this H for each H for every splitting. So in particular, if I have H1 and H2, then I get two series, epsilon H1 and epsilon H2, and they live canonically in the same vector space. So now I can take F to be the multiplication of the inverse of one with the other. So at the moment, this belongs to, again, symmetric algebra of H star, tensor UG of K with H bar parameter. And the claim is that this is a twist. So first claim is that this tensor series, at the beginning, it's valued in H star times UG of K. And if I want it to be a twist, I better make it into something valued in my algebra. And it turns out that once I do this inverse, the difference between the two is precisely now valued in UG of O. And moreover, it twists one coproduct into the other and respects associativity isomorphism. So the idea roughly is that if I take an element in GK mod G of O, I can either identify this with H1 or with H2. Then I can think of the difference as now because they're both splittings of G of O inside of G of K, their difference must be inside of G of O. And this is sort of why F is valued in UG of O. And this difference is exactly the twisting that so that twists one into the other. Great. So that's the Hopf twist. Is there any questions?
So your Hopf algebra structure, it's neither commutative nor co-commutative, or what?
No, it's neither commutative nor co-commutative. So it's not commutative. It's commutative on the symmetric algebra part, but not commutative in the universal enveloping algebra part. And it's not co-commutative in either. Unless, of course, your Lie algebra is abelian.
Okay, yeah, I'm asking because, there is this very general construction in Drinfeld paper, the original, the old one, of quantization of formal group law. So I'm just thinking whether it can be used for quantization of homogeneous spaces, again, in the formal sense, kind of. So, because if you have, it's an old story, but nevertheless, if you have the Lie algebra or Poisson-Lie group, so you can try to quantize it. That the result is, people call it quantum group. Now, if you have a homogeneous spaces, then you should say some words. Otherwise, you cannot quantize it. Poisson homogeneous spaces. Anyway, this is very old story, like 30-something years old. Goes back to Drinfeld. So basically, your choice of splitting, it's kind of a choice, if you'd like, I don't know, coordinates on the formal group G of K mod G of O. Because you identify it with H1, which is affine, infinite dimension, but still affine space.
Right.
So,
However, somehow the Poisson structure is not the Poisson homogeneous space for H.
It's not for what?
So somehow I see your question. I suppose that's if you like, it's the Poisson homogeneous Poisson structure for the Poisson homogeneous space D of K mod D of O, not G of K mod G.
Mm-hmm.
So I think
Okay.
this quantize is always the cotangent. Yeah. So because I can start with arbitrary Lie algebra, it doesn't need to have a Poisson structure.
Okay, yeah. Here you have, all right.
Yeah, but it's always, exactly. It's always this feature that if I multiply the generators by H bar, it's really quantizing this Poisson-Lie group.
Yeah.
Okay. Yeah, thanks for the question. Great. So now I have sketched you the construction of this Hopf algebra, and now it's as you can see, it's very natural. It just comes from geometry of the affine Grassmannian, and I'll also tell you how to construct the spectral R-matrix, or in Drinfeld's words, this pseudo-triangular structure, quantum spectral R-matrix. For this, I want to bring back a picture that I drew a while ago. So this picture. So physically, I explained last time that physically this equivariant after Grassmannian correspond to some four-dimensional holomorphic topological theory, and the fact that this thing should carry a spectral R matrix comes from the following physics intuition that there should be two type multiplication defined on this category. One is a genuine monoidal structure, one more akin to a vertex operator's algebra structure, and the spectral R matrix is specifically from this natural isomorphism, natural associativity condition of these two multiplications. So what we would like to do is to construct, now we are going to restrict ourselves to Yang-Yan case, which is the come from the quantization of D of O with respect to the Yang's R matrix with respect to this splitting. So what we have is that we have now a derivation, which is just del T acting on this Yang-Yan algebra. And I can define the translation operator, which is the exponential of this acting on this Yang-Yan. So this translation operator is going to be corresponding to sort of translation in a holomorphic direction. So in particular, we would like to construct a isomorphism of modules natural with respect to both entries, or in particular, or in other words, we would like to construct a universal R matrix that satisfies quantum Yang-Baxter equation and twist the coproduct into the opposite coproduct. So in the Yang-Yan case, Drinfeld sort of just wrote down this structure explicitly kind of by hand. And it turns out that in this geometric setup, it's very natural to actually construct the other vertex algebraic multiplication and a twist. So what we'll do is to construct this vertex multiplication on this representation category as well as a twist. And then our matrices will just be the combination of the twists. And this will be supplemented by, instead of a coproduct, a meromorphic coproduct, which is also something that Drinfeld constructed for Yang-Yan of a simple Lie algebra. And we'll construct a meromorphic coproduct, and the twist will become a meromorphic R matrix such that I can twist the translated coproduct into delta Z in an associative way, and my full R matrix is just going to be constructed from RS. So I'll start by telling you the construction of delta Z, which is extremely natural. Let's construct this meromorphic coproduct. So let's recall that the coproduct on my quantum algebra is constructed basically from the following embedding of ring of functions, the universal enveloping algebra into UG of K. So this is sort of the essence of the construction of this coproduct. It comes from this tensor series. And it turns out that to construct delta Z, we note that this as a vector space, I can identify this as a vector space with a vacuum Kac-Moody representation at level 0. And a feature of this vector space is that instead of having a map into UG of K, it has a map into UG of K, but with spectral parameter which is precisely the OPE. So we'll use this to define the other coproduct. So now I define a map from the symmetric algebra to symmetric algebra tensor, now with a spectral parameter in infinite inverse order by declaring that delta z applied to a function paired with a times b is just f paired with the intertwining operator, the OPE. So it's it's extremely natural construction, and on the Lie algebra part, on G of O part, we'll just use the symmetrical product. Okay, so it turns out that these two again glue into a well-defined I run out of space, so let me just put this proposition here. So it turns out that these two maps glue into a well-defined algebra homomorphism into tensor product Yang with the spectral parameter, such that it satisfies these two key properties that's akin to vertex algebras. And the first one is a weak associativity condition, which is just associativity condition, but weak here because everything depends on spectral parameter. So this is not really an equality on the nose. It's inequality after re-expansion. Similarly, it satisfies this weak commutativity condition. Right.
So does the weak associativity is the same as when you treat the vertex operator?
Yes, in fact,
algebra, and also the same as the weak commutativities if you on the diagonal.
Yes. Let me actually make two comments, and then I'll answer this question. Sorry, let me make one comment.
Go ahead.
So my comment is that this is precisely what we need to define this, because what this allows us to do is to take two modules of my Yang and then produce a third module called M tensor N, the inverse that depend on Z, and this formation of this module is associative and commutative. So this is what allows us to define this sort of a categorified vertex algebra structure. And if I choose M and N to be smooth modules, then I don't need the inverse. I can just replace by meromorphic functions on C or functions on C star. And this will be, if M and N are smooth, in the sense that higher loop modes act nilpotently, then this becomes a sheaf over C star. So this provides this meromorphic tensor structure in the sense of Soy-Bowman.
So in this case, in the non-smooth case, when you add the Z inverse,
yes,
that you permit the negative power to go to the infinite.
Yes, yeah. So I add Z inverse because to allow infinite powers of infinite positive modes. Yeah.
Sorry, just a side question. It's indeed a bit side, because you start with the Yangian. If I want to consider quantized Kac-Moody, then instead of what a differential operator on your previous slide, I should consider, instead of kind of exponent of d or dz, I should consider exponent of z dz. So it should be rescaling.
Right.
Yeah.
Yes.
Yeah. Okay.
Yeah, so you can consider these different constructions and the constructions of your usual affine quantum groups in this too. And yeah, in fact we have a upcoming work in which we consider sort of putting this, like sort of following the same idea of Eddinghoff-Kashtan and putting this kind of thing onto a curve and derive some like quantum KZ equations. But yeah, I mean, that's beyond what this thing is about, this talk, yeah.
Okay.
Yeah, thanks for the questions. And yeah, I want to give a comment about the nature of this delta Z. So unlike Drinfeld's construction in which this delta Z is not weakly co-commutative or weakly, it's not, so in Drinfeld's construction, it's only weakly associative, but not weakly commutative. The weak commutativity is again by a meromorphic braiding. But in our case, this delta Z is weakly co-commutative. This really is the linear dual of a vertex algebra structure. So you can think of symmetric algebra of G star T as the graded linear dual of V0G. That's how we define this coproduct, right? So you can also think of UG of O as the graded, actually UG of T as the graded linear dual of symmetric algebra of T inverse G star T inverse. And this now has a structure of a commutative vertex algebra. So what really the content of this proposition is really that our Yangian can be think of as the linear dual of this tensor product. And so you can in which the coproduct is the linear dual to the vertex algebra structure on this vector space. And this vertex algebra is just the tensor product vertex algebra structure. So another way to say this is that this thing has the structure of a co-algebra in the category of vertex algebras. So that's, I think, Zhongzhu's question.
So the co-algebra in the category of vertex algebras, and also what can you spell a little bit more?
Yeah, it just means that if I call this vector space curly V.
So you want the co-multiplication in a certain sense that a morphism of a vertex algebra?
Yes, so that I have a co-multiplication that is a vertex algebra map.
Okay, so this is probably something Heshen Li has also studied.
Yeah. So it's important here that I keep the affine class Moody at level 0. Otherwise, it's just not true that it's co-product.
Yes, thank you.
Yeah. Yeah, thanks for the question. So how do I understand this? Variant affine Grassmannian, this sort of double fiber product, and I get the fiber product is just this scheme, and this is actually a formal groupoid over the affine Grassmannian. It's precisely the action groupoid defining this quotient. So this vertex algebra is precisely the global section of dualizing sheaf. So this vertex algebra curly V is precisely the global section of the dualizing sheaf on this stack. So of course it has the structure of a co-algebra because it's a group. It's a groupoid over G. And it's precisely this groupoid structure that controls the equivariant sheaves on the affine Grassmannian, which is why we're considering co-modules for this co-algebra or modules for its dual, which is our Yangian. And the fact that it has a additional vertex algebra structure allows us to define this sort of OPE. So this is as much as the connection between geometry and algebra can go. As we know, the vertex algebra structure is related to the factorization algebra structure on this, where the factorization algebra structure on gauge is coming from the Bailey-Drinfeld Grassmannian. However, it's, as far as I understand, there's no way to go from a factorization category to a vertex operator category in any meaningful sense. But algebraically, this is what happens. So that's the geometry of this construction. Any questions?
So, but okay, you constructed some Hopf algebra and you have also the category of coherent sheaves on the formal completion. So what's the relation? Is it the category equivalent?
Yeah. So the relations is that the smooth modules of this, or like finite dimensional smooth modules of my Yangian evaluated one is equivalent to coherent sheaves on this formal Grassmannian. And of course, it's the same as gamma omega comodules. Yeah, I guess that's what I was trying to get at. So this is the action groupoid defined over gauge that defines this quotient. And so because everything is sufficiently affine, you can identify sheaves on this with comodules for this global section.
Yeah, somehow you restrict. I mean, you are forced to restrict to the formal neighborhood of the unit.
Right. And
kind
so
of, yeah.
Yes, and for example, if I look at the entire affine Grassmannian, the actual affine Grassmannian, I don't even know if such an intertwining operator kind of structure even exists or is meaningful.
Yeah, maybe there is another construction
Yeah.
of a Hopf algebra structure. Yeah.
Right.
But still, okay. So, and the monoidal structure on the left, it comes from this, whatever, it's a meromorphic tensor structure, if you want the braiding, in the category of modules.
Yes. So
yeah, and on the right, this formal completion, it is what?
Yeah, so there are two monoidal structures, right? So one of them is just coming from the coproduct of this. One of them comes from coproduct of this, which correspond to the convolution monoidal structure on this.
Yeah.
Another is a vertex monoidal structure, a meromorphic monoidal structure, which we constructed basically by saying that the factorization structure, or the other words, that this thing also has a compatible vertex algebra structure. The other monoidal structure is constructed that way. And what I will tell you is that these two are actually compatible in the sense that there's a braiding that relates them.
So then, and you don't know what's the analog of the second one for the full Grassmannian?
I don't know.
Yeah. Okay.
I mean, so basically, it should. I don't think there is one, just because somehow. So if I have a chiral algebra, the way I can get to a vertex algebra is to use some six-functor formalism. You need to use the fact that the D modules over curves can have a lot of functoriality to construct sort of a specialization map. And I mean, I don't think this kind of thing exists with categories.
Okay, yeah, it's an interesting question. Yeah, okay.
Right. Let me now say that how do I construct Rs of Z? Now let's see. So again, let's recall that the important thing for constructing the ordinary coproduct is this embedding, and from this embedding, I get a tensor series, which is an element in here. And this tensor series was used to twist Hopf algebras. And it turns out that this will be useful too. So now the other monoidal structure was defined by this embedding, which is the intertwining operator map. And again, I can think of this such an embedding as a tensor series, which I'm going to call Y, which belong to this vector space. Now it's the same vector space, but now with Z plus minus parameter. We can write out E pretty explicitly. Because it's just a universal enveloping algebra, so it's group-like. So we can write out this E. Actually, I haven't defined E of Z. E of Z is just the translation of E. I can write this down very explicitly as in the following. It's very similar to Drinfeld's. Well, this is just the R matrix. So here I take TA to be a set of bases for G star, and the XA to be dual bases in G. I can write down this tensor series where T1 and T2 are the parameters inside of this loop, and Z is this extra spectral parameter. And I translate this tensor and expand over the region where T2 is large. So I expand over negative powers of T so that my T1 can be positive. And of course, Z is also positive translations. Now, this tensor series Rs that I will use to twist the two coproducts is exactly the same form with a minus sign. It's just the same tensor series with a minus sign, but now I'm going to expand this over a different region because we would like this to remain in my algebra in order to be a meaningful tensor. So now if I expand this over the region where Z is large, then my series in T1 and T2 are both positive. So in particular, this is by construction an element in the following tensor space. And in particular, it belongs to our algebra now, and so it's a meaningful twist. So the main observation of this construction, well, the main construction of the main statement here is that this RS serves as a way to twist between the two coproducts because it serves a way to connect multiplication and OPE in this formula. So in the sense that RS is the missing piece between epsilon Z, which is defining multiplication, defining this sort of universal enveloping algebra embedding, and the OPE, which is defining sort of this chiral embedding. And of course, to write this down, one needs to be careful.
So those delta Z's actually depending on two parameters, T1 and T2.
Oh, T1 and T2 should be thought of as sort of the loop parameter. So if you see, say,
yes,
T1
there are two different loop parameters.
Yeah. So I should say XA T to the N to me is XAN, TA T to the N is TAN. Sorry about this multiple use of T's. Right. So one needs to make sense of this multiplication because epsilon z has infinite series in positive z, and the RS of z has infinite series in z inverse. So in a priori, this multiplication doesn't make sense. It makes sense in a sort of formal completed way, and this is precisely locality. Because in this multiplication, I'm putting annihilation operators always in front of creation parameters, so creation operators. I'm always putting positive modes of G of K over negative modes G of K, which is why this multiplication makes sense, and this multiplication precisely gives me intertwining operator. And because of this relation, RS sets grades the coproduct of one of the coproduct into the other, and it satisfies the following as sort of spectral version of associativity condition. And let me just comment that the associativity condition actually follows from the following conditions on epsilon y. We already see that epsilon satisfies this condition that delta tensor 1 epsilon is epsilon 1 3 epsilon 2 3. It turns out that y satisfies a similar condition like that. And the first condition, as we talked about, is this is just saying that my embedding is a map of algebras. And this is precisely the associativity condition. It's the OPE. So this is equivalent to the conditions that YAZ plus W YBW is YAZ BW. So it turns out that these two conditions are satisfied by epsilon y forces R to satisfy this cocycle condition, which is the associativity. Great. Corollary.
So I don't understand the delta here. Is that sort of co-multiplication corresponding to co-multiplication in the category of vertex set?
So the first.
So is this of a co-associativity or associativity? It looks that you're saying here is actually the weak associativity in the OPE sense.
So here the coproduct, the first factor of both epsilon and y belong to the symmetrical algebra. And this symmetrical algebra has two coproducts. One is just the ordinary coproduct coming from the fact that it's dual of an algebra. The second is a vertex coproduct coming from the fact that it's the dual of a vertex algebra. And so this is the coproduct in the first sense. It's just the statement that epsilon AB is epsilon A, epsilon B.
Okay.
And the second one is precisely the similar statement for intertwining operators. Yeah, that's does that answer your question?
Thank you.
Yeah, no problem. So from this, then one construct as a corollary that if I set R of Z to be just this R21 inverse R with this spectral parameter, then this R of Z will permute the coproduct into the opposite coproduct and satisfy quantum Yang-Baxter equation. And it's a pseudo-triangular structure because it's sort of triangular. Okay, so I think it's already 12, so I probably don't have time to go to dynamification. I want to end with maybe some comments more about geometry and some speculations. But before that, is there any questions?
If your time permits, you could talk about, I try to get a feeling of this constructions, talk about the correlation functions or.
Sorry, I can't hear you very well again.
But the correlation functions, so this kind of Yang-Baxter, whether that's how that's related. So I try to sense that Yang-Baxter are the actual vertex algebras or some things that correspond to the correlation functions, or that's irrelevant. So you decide.
Correlation functions.
Mm-hmm.
Like how it's related to these like spin chains or?
Uh-huh.
Yeah. So, I guess that's probably related to the following. What I want to talk about in geometry. So the idea of like constructing these. So Kevin's original idea of constructing, relating these four-dimensional theory with two integrable systems is precisely start with your four-dimensional theory and do a dimensional reduction along a curve. You get a 2D integrable system with spectral parameter on this curve, and you insert line operators, and that there you get basically your sides of your 2D integrable system, and that's precisely how this R matrix is related to your Euro spin chains. And he shows that because he showed that at the end the 40th theory is controlled by Yang, so it's the 2D reduction is related to spin chains. Is that your question?
Yes.
Okay.
Yes, you can go ahead.
Yeah. So let me give some comments to geometry. So some more comments on geometry. Mainly, again, related to this dimensional reduction idea. So how did we construct this Hopf algebra? How did we construct this splitting is we take the splitting of this Lie algebra. And if you are familiar with this kind of thing, this splitting is precisely sort of the cohomology calculation of a sheaf of Lie algebra on P1. This is the sheaf of Lie algebra. Let's call it G infinity. It's G infinity because this is precisely the sections of the sheaf Lie algebra is just sections of the trivial Lie algebra, except that I require this section to vanish at infinity. And since I have a sheaf of Lie algebra, since I'm always in a formal setting, in some sense, you can think that the formal completion of this sheaf of Lie algebra is a formal group bundle. Over P1, so that the splitting condition is precisely equivalent to the condition that the associated Lie algebra, which is just the starting Lie algebra itself, has zero cohomology. And this cohomology is precisely controlling the tangent space of this formal group bundle in the space of G bundles, formal group bundles on P. So in some sense, the fiber functor which is constructed by sort of acting on this double quotient is precisely, in some sense, this is a local Hacker modification on at this point. So you can identify this double quotient with the formal completion of this formal group bundle in the space of G hat bundles. And the fact that this is cohomology is trivial is this statement that locally at this formal group bundle, there's no moduli. This moduli space of G hat bundles locally at this point is just a point. So fiber functor is constructed is really just a Hecke, is given by Hecke modification in some sense. So in this formal setting, then you can play the same game. You can pick multiple points, and the cohomology is still of the sheaf of the algebra is still trivial. So even if you take multiple points, you still get a fiber functor, and in some sense, there's nothing interesting for this Hecke modification. So physically, this in some sense this is a dimensional reduction of my 4D theory along my P1, and with some singularity configuration defined by this sheaf of the algebra.
But in your setting, you can consider only reduction. I mean, choose just one point, or can you?
I only need to because I'm looking at formal completion at a point. It's always preserve a formal neighborhood.
Yeah.
Yeah. Is that your question?
Yes. Yes.
Yeah. Thank you. Yeah, thanks for the question. And so this fiber functor in the setting of 4D transimus theory is precisely what Kevin used to realize Yang-Yin. So in general, if I have a simple Lie algebra, there are many splittings, and they're supplied by classical generalized R matrix. So let's pick R to be a classical generalized R matrix in the sense that it's an element of the form is an element in this vector space, which satisfies a generalized Yang-Baxter equation, and it's not necessarily skew symmetric. So given such a generalized R matrix, one still gets a splitting of Lie algebras. It's always a splitting of Lie algebras, and it becomes a splitting of Lie algebra if you remove this generalized. So if R satisfies skew symmetry, then this is a splitting of Lie algebras. But we don't need that because we just need a splitting of Lie algebra in our setting. This induces a splitting of the cotangent. So D of K is T of O plus the conormal of G of R. The R matrix of D of O, it's precisely a skew symmetrization. So I started with some generalized R matrix, not skew symmetric. I apply a skew symmetrization. It's the skew symmetrization of your generalized R matrix. So the following is what I learned from my collaborator, that basically from the geometrization of Belavy and Drinfeld is that such an R is associated to such an R is always a curve of genus less than or equal to 1 and a sheaf of Lie algebra, which specifies the singularity of this R matrix, such that if you choose a generic point and choose the formal neighborhood, then you can identify this with G of K. You can identify the formal neighborhood section over the formal neighborhood with G of O, and you can identify with identify the sort of the section away from this point as G of R. So of R matrices and due to Bella-Witten and Greenfeld. And just in the same fashion, the fiber functor associated to these R's correspond to the action of this Hackett type action, which again, you can identify with formal group bundles on this curve I formally completed at this point, which is just a point. Because splitting again is related to how cohomology is trivial. So this also has a geometric meaning in the sense that now you don't necessarily need to choose P1. You can choose a genus less than or equal to 1 curve, choose one of the sheaf of Lie algebras which specify the singularity profile and do a dimensional reduction. So now everything so far seems like it's all just a formal group and formal Lie algebras, and it turns out at least in this algebraic setting we can do more. And I won't go into detail because we're already out of time. I'll just stop. I'll just say it real quick that my sheaf of Lie algebra, my double quotient, if I require the action of G of O to integrate to a group action, then it not only acts on the formal group bundle, it acts on actual G bundles. Now you can pick any curve and any group. When a genus is larger than 1, then by the work of Bayes and Greenfeld, you're not going to be able to get any splittings. Like there's every bundle we're gonna come with some non-trivial moduli. From the physics work of Costello, Witten, and Yamazaki, one expect that in such case one can get a dynamical system on bound G. This action can lead to a dynamical system on bound G. So our result with my second work with Abedin Rashid is that suppose I choose a point in bound G that is regularly stable, in a sense that the stabilizer of P is just the center of the group. In this case, locally over this point, my moduli space is actually a torsor over an affine variety. Over a smooth affine variety. These are not theorems. These are just facts. And the theorem part of this is that if I formally complete this coarse moduli space over P, and think of this as an sort of an affine variety, a formal affine variety with some variable, then there exists a dynamical twist F on Yang valued in this lambda, and we can use this twist to get this is a solution of a dynamical Yang-Baxter equation. So this dynamical twist should control a Hackett modification of my affine Grassmannian, formal affine Grassmannian locally at this point, and this dynamical R matrix controls the braiding, the spectral braiding locally at this point. So so that's sort of this theorem is the content of our second paper. So that these are things I want to comment about geometry. I want to end with some questions that I'd like to understand, but not, I don't. So speculations. So the first one is that in the work of Curtis-Williams, they started with not just this formal Grassmannian, they started with the entire affine Grassmannian, but they were not able to get a full R matrix. They just get a renormalized R matrix. As we talked about, I think last time, this renormalized R matrix should be the most singular part of the full R matrix. And I don't know if this is possible, but I wonder if in this geometric setting, one can actually define a full R matrix over the entire affine Grassmannian rather than just at this formal neighborhood of identity. And
it's still meromorphic, yeah.
Yeah, it still would be meromorphic. Still be spectral. And the second is, this is even more mysterious to me, that apparently there is some string theory or six-dimensional theory set up somehow says that the monoidal category of line operators in this theory, at least for superconformal theories, should be defined by modules of some cohomological Hall algebra associated to a quiver. To the quiver underlying the cluster structure of this category, and this coha is what defined by Kontsevich-Sobelman as the algebra BPS states. And I mean, I was told that these line operators would be modules for these BPS algebras, and I mean, so far I have not been able to understand how to even build a connection between these two, and also this coha should have very interesting algebraic structures. For example, this should have like a meromorphic coproduct, and it would be interesting to see if there's a spectral R matrix that one can cook up from these cohas.
Yeah, but probably you know that work of David with Grigoriev, and I forgot who was the third one. Yeah, they think that it should be a category of line operators should be a category of bimodules over coha for associated with this BPS quiver, but probably mathematically indeed it's better to think that if you somehow constructed this monoidal category, and if again somehow you proved that at least its Grothendieck group K0 has a cluster structure, which is, as far as I know, it's not a theorem in general. Yeah, then you can get the quiver, and I understand that David wants to put a generic potential, because Koha, it's better to have not just quiver, but quiver with a potential. And for cluster structure, you need you want to have a possibility for infinitely many mutations of this data, and so it should be generic potential, kind of a potential from the open subset in the space of open. All right. So first, I do not quite understand how to construct these quivers. In those cases when I do understand, I do not understand how to construct the monoidal category. For example, for theories of class S, this quiver, it's basically Fock and Goncharov story. Quiver and the potential, which is generic, comes from triangulations of your surface, ideal triangulations of your surface. Yeah, but then the question is about this monoidal category. You probably know the literature. I mean, as for the algebra, yeah, there is some work of Allegretti and Chan. They constructed cluster. I mean, they related the cluster structure of Cautis and Williams to some special cases, I think. Up to 4 points on CP1. I don't remember the world record in this direction, but the question is how to quantize the corresponding, I mean, how to categorify the corresponding skein algebra, yeah? And yeah, I have some kind of ideas what can be useful, but I think it's kind of quite terrible. I mean, there is some work, but from pure topologists on quantization on categorification of skein algebras, but it's use so different language that it's difficult to compare. Okay, so yeah, so that's about this Koha business. Yeah, it's interesting. Yeah, I have some kind of running project with with Gufang Zhao, Yaping Yang, and Rio, yeah. Which might be related in the end to this, which should be related, but that's the question is at what level of rigor you want to get it. So I want to construct it mathematically, so and therefore kind of yeah.
Yeah, I understand. It's a hard question. I mean, there is a question of whether even like what, because your Koha is not in general not a Hopf algebra, and the way Gaussian always. Sorry.
Yeah, you're right, but in some cases there is some I would say associated to it like spherical some algebras which are closely related, which in the end turns out to be ordinary Hopf algebras, but for a mysterious reason, some
But
consolation
also
of poles.
taking spherical part seem to be, I don't know what kind of operation this is, because like Koha is what you use to for example define Shor index, calculate Shor index. If you take the spherical part, it might not necessarily correspond to the correct physics theory.
Yeah, so then when it comes to physics, I always believe to what physicists say. I mean, yeah, but sometimes the spherical part is not bad. I remember we wrote another paper with Gufang Yaping and Mario Rabchak. He was a student of David. And we constructed the action of Koha on actually of even of a double of Koha on this cohomology of the Nekrasov spiked instantons. You know that story because, in perimeter, there are many people to talk about it. Yeah, but the thing is that at some point, when we wanted this vertex algebra at the corner acting on this cohomology, we went to the spherical part. So then it was useful there, and it had really a coproduct, not just a meromorphic one. But yeah, you can work with the full Koha and meromorphic coproduct, and maybe it's not wrong.
Yeah, the
Because
reason I think of that is because sort of in your usual Yang-Yan, right, it contains the Borel part, and it also contains the nilpotent part. And the nilpotent part is not a Hopf subalgebra, but it is a vertex Hopf subalgebra. So that the Drinfeld coproduct does not restrict to n plus, but the meromorphic part does. And this has a similar statement in Kohas, where the Koha does not have a meromorphic coproduct, does not have a coproduct, but if you somehow manage to add some carton, then you can write down a coproduct. And in this case, one can consider this as some sort of a mixed bialgebra. It's an algebra in the category of modules for the quantum for the torus, together with a meromorphic coproduct. And it's likely that you can so you can think about this n plus part as an algebra in the category of modules for T. And it's not a co-algebra object, but it's a meromorphic co-algebra object if you use the meromorphic tensor product. So in some sense, it's still kind of a co-bialgebra, but with respect to these two different monoidal structures. And somehow, when you consider modules of the Yang-Yan, you're not considering full modules for n plus, but I think in some sense of meromorphic co-module. So you can't get double Yang-Yan as a double of this, but it feels like it's more close. It looks more like a meromorphic version of the double.
Yes, this makes sense, especially if you think in terms of holomorphic topological field. I mean, you don't want to get rid of this meromorphic part.
In some sense, for Koha, I always thought that you shouldn't just consider bimodules for Koha, but really maybe some mixed.
Yes, of course. I told this to David a long time ago, but he somehow believes that it should be bimodules. I don't know why. But anyway, so I have a different, I would rather agree with you that it should be, he told me that something doesn't match.
Yes.
That's what I forgot what. Certainly he knows your work and but he said that something and I believe they have even an appendix maybe about usual Yangians in their paper, I forgot, but something indeed. I believe that it should be rather well. First, I'm not sure that it has to be really the Hopfeld, but if it is a Hopfelder, it would be rather with meromorphic coproduct. Yeah, it can be very much. Yeah. Okay, more questions?
Yes, I do have a question. In your construction of Yang, somehow you get involved with the vertex algebra corresponding to the finite dimensional Lie algebra.
Yes.
The VG or V0G. So do you care about, is this, I'm sure it's the universal vertex algebra. Do you care about the level?
Actually, yes,
or
the
you're
level.
at a critical level.
So the level has to be 0. This kind of confused me a little bit too, but the level here has to be 0 because otherwise otherwise this does not have a meaningful co-algebra structure. Your co-product is not a map of vertex algebra unless it's at
I see.
level
So that's a V sub 0 here means level 0.
And somehow this fact that this level is not critical also has something to do with framing anomaly. So my Yangian actually satisfy the following. Like the ordinary Yangian satisfy this relation that if you square the antipode, you take your, let's say just GL Yangian. So I have this like RTT presentation. This is the same as U plus H bar the critical H check, the critical shift by critical level. So in the same way, this Yangian satisfies the same property. If I square my antipode, then it doesn't send if I square antipode for the symmetric algebra, it remains the symmetric algebra. But if I square the antipode for the commutative, for the Lie algebra, it becomes x plus some h check t. So you see this kind of, because I'm not at critical level, there is, so there's some translation going on. Yeah.
What I even more interested in was this V0 is the universal vertex algebra, because corresponding to the level 0, you have two different vertex algebras. And there is an irreducible quotient. In this case, the irreducible quotient is just the one-dimensional boring vertex algebra.
It's not interesting,
yeah. But what happens if you do at the level and some of the coalgebra structure may fail, but could it possibly be a comodule on the level 0 side?
If I don't have, well, this is an interesting question. So if I don't at level, if I add the level,
yes,
I cannot define this to. I suppose you can always define this kind of multiplication.
That's right. Yeah.
And
in particular, you take one of them to be 0, level 0, and that's what you're dealing with. Yeah, for each one of those, you will have simple ones. But
that's a good question. I mean, this should be related to your affine Grassmannian has a multiplicative line bundle, and this pullback structure is specifically related to the structure of this multiplicative line bundle, at least for integer levels, positive integer levels. So each of this is so I have this G with this equivariant line bundle, and I can go through this monoidal structure, and this monoidal structure will just say that this line bundle multiply. And this map is precisely the pullback of the space of distributions. This is as much as I can say. I don't know if anything.
I see. Okay. So this is actually this is the picture of here you're taking a line bundle. That's interesting. There is a level rank duality
Right.
So that will be corresponding to the algebra. Here, the non-model is basically turning the powers of the non-model, turning the level.
Yeah.
I see. Okay, well, thank you very much. It's very interesting. I'm sorry I missed your first talk.
Oh, of course.
It was my fault because get used to Thursdays.
Wow.
Okay, are there any more questions? Well, if not, thank you very much. Thank you,
Thank you for
Wenjun.
inviting me.
Yeah, and I ask you, as I did last time, to send me the notes of your talk so we can post them.
Yes.
Okay, thank you. Thank you very much. And this is it for today.